Welcome to another lesson with Tacoa Lawson. I'm working through the AP Physics 1 curriculum with you. As you can see in this first slide, it's just a title slide. We're looking at the Introduction to AP Physics 1, which is our first unit. You should have already watched the video on the big ideas, and these are a little more introductory stuff. Nothing that's too heavy or nothing that you're going to be held ultimately responsible for. You'll probably find most of this material is actually a review from other science courses you've already taken, assuming you've taken science, at least chemistry, biology, or something else before entering this class. So we're going to start off this lesson with the nature of science. It's really about how science is a unique content knowledge area. Science is unique in a couple of little ways. We'll go over those details. I don't want to give away too much. Scientific knowledge is built upon a unique set of principles. Some of those specific areas that separate science knowledge from other types of knowledge are things like that it's actually attempting to explain the universe we live in. There's a lot of different philosophies and a lot of different areas that would be thinking about the universe we live in, but they aren't necessarily trying to explain it. Some of them might come up with different reasons for why things are, which is okay. But the difference about just thinking about it is that all of the thoughts that science produces have to be testable. That'll come up in a second when we talk about the third bullet point here. One of the other things that's unique to science is that it's based on theories which are based on actual experimental evidence, not based simply on opinion, but a series of experiments, a series of data collection, a series of real information that has to be collected, and even more importantly, has to be able to be collected by different people in different locations and be what we refer to as verifiable, has to be repeatable. All science, doesn't matter where you do it, if it's truly explaining some part of the universe, since the universe seems to be the same in all parts, or at least we believe so at this point in life, science experimental data should be the same in all parts, assuming you have similar access to technology or other resources that are needed. One of the things that's very different, and I guess in some cases you might find some subjects like math have a little bit of relationship. Math doesn't tend to have experimental evidence that's supported, but it has to have proofs and other different ways in which it's data that's not straightforward, can be verified. But science has to be falsifiable, which means really more than proving something is true in science, we're always trying to come up with ways to test to determine if it could be false. Because a good experiment says, well, if you have this theory and it makes this claim or this prediction, if I can prove that prediction wrong, then the theory can't be accurate either. So oftentimes we're really trying to test and prove that what you have as a theory is not true. And the more and more ways you kind of come up with things that if it wasn't true, this would happen, then you get more and more support claiming that if you can't prove it wrong, then it starts to become a little bit more likely, you become a little more confident that it's more right than wrong. But of course, as has happened throughout history, sometimes we have a theory, we have something that's developed, something that seems to be true, new technology, new information, resources come, and then they end up giving us a new experiment, which turns out to disprove or falsify that theory. Sometimes it has to be completely scrapped, and other times it just has to be tweaked in a way that allows this new data, this new information, to be incorporated or become part of it. We're, of course, working through the AP Physics curriculum, so that's where our focus is going to be once we get through some of this housekeeping bit. What students often ask is, why take physics? What good is physics? Where's physics knowledge going to lead me in the future? And the truth is, physics is related to almost every field, probably most professions, some which are obvious, things like health and medicine, some which are not so obvious, related to musicians and musical careers. But there are lots and lots of different areas that use physics. And you'd even be surprised, there's a lot of people with physics degrees or people who majored in physics or other mathematically based science-like courses who end up working in business, or end up being in Wall Street, or can end up being in any number of different careers because that problem solving, that analytical, the ability to look through data sets, the ability to organize information, all of that will serve them well in many, many different disciplines. So we're going to look at a couple of those different disciplines right now. Since physics really is about understanding the universe we live in, its real focus is trying to understand the parts of the universe, which are basically matter and or energy. And then, since matter and energy exist and they have the ability to interact, we of course want to understand what those interactions entail What is it that makes it so some interactions are possible and other ones are not? Even though those are all a very specific area, the skills we work on, the ability to memorize information, the ability to reason through different problems, the ability to come up with a solution that might be multi-step or end up taking multiple steps to get to the end, are all skills that will serve you in a lot of different areas. So while we're really focused on explaining the universe and the laws that govern it, other fields, obviously, sciences take advantage of it because it's their nature to use the science. Physics is referred to as the core science because all other science disciplines lean on physics to explain how certain things happen. Other areas that are physics related are things like architecture and engineering. Any type of career in architecture and engineering, you have to understand a lot of the fundamental laws of physics, either in how forces operate, how different materials will behave under different circumstances. Every one of those situations becomes very, very important when you have buildings or bridges or other large structures that could end up being disastrous if it's not done or if it's not taken care of with full knowledge of the physics relationships, either in terms of materials or forces, how people utilizing the object that's being produced might end up affecting it. Art is not quite as obvious, but there's a lot of different physics in different art installations, especially when they're doing some of the different balancing techniques, or when they're looking at the way in which light might interact with different materials. Music is an obvious one. Every musical instrument has physics related to how it's able to produce harmonious sounds, how you're able to get different keys or different octaves off of it. And anyone who does any tuning of any instruments, things like tuning pianos or tuning other instruments, you are utilizing physics. You are utilizing physics skills, and having an understanding of the physics behind the instrument that you're tuning will give you a better ability to be able to service it, not to mention just to be able to be more analytical and more reasonable while you're doing it. Medicine is an obvious one. Anyone who's thinking about any related field, you're definitely going to want to take physics in high school. Taking AP Physics is a great plan. You'll definitely be taking that in college, and having a little background before having to compete with other students in that course at college will give you a leg up on the competition and put you in a better situation to be successful. And then, of course, technology, whether you're doing something that's related to computers, computer science, whether you're looking at app development, whether you're looking at any other kind of computer or technology related field, physics will definitely be involved in understanding the principles, being able to do problem solving, being able to collaborate with others. All those different areas will be very important. The last area we're going to get into is models, theories, and laws, mainly because before we start getting into some of the more brass tacks kind of foundational skills that you need to have, and what will probably feel more like a physics class to you, we just want to make sure it's clear what these three terms mean. You will hear all three vocabulary terms used often throughout class and in these different videos. Sometimes students will think that they're synonymous, and the model, the theory, and the law all mean the same thing. And they are all related. They all relate to some kind of scientific knowledge, some kind of scientific understanding. Absolutely true. And in some cases, the differences can be subtle, but they are not the same thing. Looking at models first, models are an analogy or an image of some kind of phenomenon being examined. They are usually pretty simple in structure. When we have a model, the whole idea of a good model is that you keep it simple. One of the weird things that sometimes happens is that means you ignore some truth, some known aspect of it. For instance, we have the model of the globe. The model of the globe is actually a sphere, right? We say, oh, the Earth is a sphere, but it's not. The actual shape is, and it's kind of egg-shaped. So why don't we make the globes egg-shaped? Well, that detail, while important, if you're truly understanding the nature of the Earth and how the forces are acting on it, is not necessary to understand it for what we use the globe for, which is simply a map to be able to show the geographical location and where something is relative to something else, or to be able to make plans for a trip, or to just simply be able to understand time zones or longitude and latitude. All of those different things can be done on a sphere just as easily as an egg-shaped globe, and a sphere is a little bit easier to produce. A sphere is a little bit easier if you're going to have on something that's going to rotate, and so it turns out to be the beneficial model when we're doing it for certain activities. However, if we wanted a model that was more precise or showed greater accuracy to the true shape of the Earth, it would not be sphere. One of the things between that's different between a model and a theory is more detailed than the model, and it describes some kind of phenomenon or gives some kind of testable prediction. And that's the big difference. A model simply shows or demonstrates the structure that we believe to be true. A theory gets a little deeper understanding, gets into what is it about, what is responsible. For instance, if we go back to the globe, why is it that it's egg shaped? It turns out that because of its rotation, the forces that are acting on it at the equator are not the same as the forces that are acting on it poles, either the North Pole or the South Pole. And because there are different forces as it rotates, that ends up causing it to have a little bit of a different experience through that axis, and therefore get stretched out and not be a perfect sphere. Laws are more generalizations than theories. They're kind of the bigger picture. So, for instance, there's the atomic theory, which gives some idea to the structure of the atom. Right? It's a good model. It shows where the different parts are. It's a little bit more than just a model because it's been testable. We're able to test whether or not there's a central bound nucleus. That's the Rutherford-Coyle experiment. We're able to test whether or not you can charge them in a number of ways, whether using friction or electricity. And each one of those different verifiable things makes it so that we have this really strong atomic theory. However, the atomic theory is not the atomic law, because even though we have a lot of supporting evidence, even though there's a lot of things that suggest that atoms exist, it hasn't quite got that completely general statement. It hasn't quite been generalized well enough to become a law. Laws are much more general statements, things like the law of conservation of energy. We have done lots and lots of different experiments. We have tested how energy is converted from one form to another, how you can transfer energy from one place to another. And in every one of those cases, no energy has come into existence or disappeared from existence. It's always been accountable. Same with the idea of the law of conservation of matter. When we measure the amount of material we start with before we burn something or before we react it in some way, then we measure all the different products that are produced. We always get the same mass of material we start with and the mass of material we end with. And it doesn't matter how many different ways we test it, we always get that same result, which is why that's the law of conservation of matter. So laws are a little bit more advanced than theories simply because they've been tested over a much larger range. They become much, much more confident that they will never be proven wrong. And remember, that's one of the things that's unique about science. Science says things have to be falsifiable. You start by kind of coming up with a model, you do some predictions, you get some data. Once you have some data on your model, if it seems to be hard to prove wrong, or if there's supporting evidence by not being able to prove it wrong, it steps into being a theory, then that theory has to stand the test of time and has to be tested far more than just one way. And as we get lots and lots and lots of different ways of coming up with falsifiable experiments, then we get more and more information. And eventually, if there is enough confidence that it will never be proven wrong, then we'll go ahead and graduate that into the law realm of science. Here we see two specific models. I already mentioned one, the model of the Earth. Nice sphere there, even though it's not, we know it's not. But that model is perfectly usable. There are very few things that the sphere model will not work for. So one of the things about the model is that it has to be able to share important characteristics. Whatever it is we're trying to analyze or describe have to be visible or have to be present in the model so we can use it when we're trying to give information to other people. The other image that you see, so here of course, there's our model of the globe. Pretty sure that's obvious. I don't know why I felt the need to point that out to you. But over here we see the model of the cell. Now, the cell is a very, very important model. We saw the cell for the first time a few hundred years ago when it was first starting to be analyzed. However, in the time between then and now, the structures inside the cell, we've gotten more and more information about it. And this model that's shown here has all of those different parts identified. Different things like whether or not you see the mitochondria or the centrioles, or the nucleus or the nucleolus, or the Golgi complex or the endoplasmic reticulum. Every one of those is a different structure inside of that model. So that model allows us to identify the parts of the cell based on the diagram, and oftentimes the model actually even relates the different parts to each other, and we do have functional parts to this model. We could also look at things like a plant cell, this is an animal cell, and see how that model is different because plant cells have some unique characteristics that are not the same as animal cells. So any model, whether it's Earth or a cell, has to have characteristics that match what it is that it's describing. It doesn't have to be perfect, but it has to be a good general picture, or if it's really imperfect, it has to be good in the sense of what it is we need it to describe. When we take a look at theories, theories are that more advanced statement. Here we see some about the atomic theory. On the right-hand side, you see the model for a fluorine atom. And we know it's a fluorine atom because it has 9 protons and 9 electrons. In order to be a fluorine ion, it would have to have more electrons or less electrons than it does protons. Now, the fluorine atom has some important structural parts. Here we see the nucleus, which contains the protons and neutrons. That's a good thing about this model. We see the first shell, which contains 2 electrons, and we see the second shell, which contains 7 electrons. This model allows us to see that there's a central nucleus that contains all of the mass, the protons and neutrons, and there's shells of electrons at different locations as we move away from the nucleus that contain different amounts of electrons. This is a great model for being able to visualize or see these basic parts, mainly the nucleus and the electron shells of the atom. If we compare that model with the model on the left, which is a little bit more of a simplified model, that model still shows a lot of the same information. What we see here is there's a nucleus that contains protons and neutrons. This model has the advantage. The protons and neutrons are more clear. Over here, we kind of only see the protons. They're all either the same shade, so we can't really tell that one's positive and one's neutral, or they aren't showing the neutrons, which would be a bad model because the neutrons are important. Now, you could make an argument if you're going to show the charge of the atom or the ion, that neutrons are neutral, so you don't need to show that. Model that works for what you're trying to explain depends on what you're looking at for that scientific phenomenon. On the left side, we see a model that includes protons and neutrons clearly shown in the nucleus and shows the electrons around the nucleus. But this model doesn't show that the electrons have different energy levels in terms of distance from the nucleus. It shows them kind of existing in these orbits that I was talking about previously, which is actually a terrible model. However, if all we're trying to do is show the general location of the different subatomic particles, where in the atom you'd find the protons, neutrons, and electrons, then showing them in these shells or showing them at different distances ends up muddying the model or making it harder to understand the basic principle, which is these 3 particles make up the atom. We have great confidence in the atomic theory because of the number of different experiments that have been done to evaluate whether or not matter is composed of smallest parts. Whether we talk about chemical analysis or physical analysis, all experimentation we've done suggests that there are smallest pieces of an atom. This theory, which has been supported by lots of different evidence by testing whether or not matter is made up of smallest pieces, mainly in how they either chemically or physically behave with each other, we have great confidence that this theory of atoms, or the atomic theory, is accurate. To close, we're going to talk about laws. Laws are much more general, but much more rigorously tested than theories and models, of course. A law is built up over a large amount of time, or at least, even if it's a short period of time, a large amount of data, a large amount of experimentation. And it gives a very descriptive statement, or a very general descriptive statement about the behavior of the universe. We literally in physics are interested in knowing the laws of the universe. What is it that governs how our universe operates? And so that's why we look at these descriptive statements. They usually have some kind of cause and effect relationship. And so the best law gives us that relationship. For instance, Newton's second law. Newton's second law states that a larger force acting on the same mass will give a greater acceleration. In all of the tests of forces and acceleration, we have yet to find one instance where a smaller force gave a larger acceleration. And because of that, we became very confident, and technically they started out as 4 laws of motion, But they, like all science, especially when it comes to science, first kind of being illuminated, and Newton was lighthouse in his field. He discovered a lot of things that people hadn't really thought about or figured out before him, and that we've still been trying to make sense out of. But he saw that the greater the force, the greater acceleration, and through rigorous testing, became confident that there was no instance in the universe where that wasn't true.